into it. So today's CPD really, the focus of this CPD is we're going to look closely at internal insulation solutions that are appropriate and considered low risk when you use them in traditional buildings. So typically traditional buildings is defined by, your pre-1940s building stock, which is really largely outside the scope of the Code of Practice NSCI SR 54. So these are the types of insulation methods that you need to use in sensible building upgrades where a building might be very sensitive to moisture-related defects and things like that. So with that in mind, a lot of what we look at is related to moisture, its impact, the primary drivers that cause it, its relationship with the walls, and how it might affect the insulation systems. So we do that, and we tie it into case studies as we go, and before we get to the end where we'll have time for some questions. And what you'll see really as we go through it is, presenting over the next 4 slides, I'll show 4 different insulation methods just to start with. And that's really just to set the tone to show you that there's no silver bullet when it comes to these older buildings. Very often the correct installation method will really come down to the conditions that you find in each case. I often heard the phrase, buildings are like fingerprints, and that's very, very true. And a lot of your members will be very aware of that as well. So for example, in this case here in the Regency refurbishment, this building had some beneath ground features. So it had some sub-basement level, it had external renders, it had some ongoing moisture-related defects. So in this instance, they opted for calcitherm, and we'll explain why as we go further through it. In the next building, again, it's a single leaf structure, but in this case, it was an old stone barn, and it had huge volume or space internally. So that was one of its, considerations. They looked for very low U values, so simply applying a 50 mil board to the wall wasn't going to cut the mustard. And crucially, they were going for an external plaster, which meant the building would have been potentially in a very weather-tight state. So in this case, they went for a dry line with a vapor control layer internally. In the next building, it's also a single leaf building, but in this instance, they had external lime plaster and internal lime plaster. So it was quicker and cheaper, more cost-effective to simply apply a wood fiber board directly to that and call it done. So as you can see, every time you're looking at a new building, you're dealing with a different set of circumstances. So what fits for one building might not necessarily fit in the next. And just to really hammer home that point, here's another old single leaf building, but in this case, it didn't have any internal surfaces. It just had exposed masonry. So there was a great advantage to being able to insulate this building and level it at the same time using a thermal plaster, like diatomite, some of you might be aware of, which is it's a cork and lime-based insulating plaster. So in this instance, they just directly applied that plaster to the exposed stone wall with a plaster pump machine to an overall thickness of about between 50 mil and 70 mil, significantly improving the performance of the walls for insulating quality and airtight quality, I might add. So as you can see, it's a sensible way or a sensitive way to approach an older building like that and help maintain some of the original features, which you'll see on the bottom right-hand slide. They're able to mold and curve and finish it beautifully. So it maintained that historical character. So there's 4 different buildings, and we'll go through loads of other buildings as we go, but in each case, they use something different. And, the performance attributes of those materials are all very, very similar. They're all breathable, but they behave in different ways. So we'll look into that in more detail. So the reason we want to get it right is that a poor approach to these older buildings, everyone can read, so I'm not going to read it all, but you just pick out the red words, as just one way of looking at it. If you pick the wrong thing, it tends to lead to things like decay, rot, failure, mold, cold, and health risks. So those are all the things we want to avoid. Those are all the things that are compounded by moisture in buildings. And moisture, of course, can come from multiple sources. It can come from outside. It can come from inside. So it comes from the rain, it gets in behind your plaster or through a building defect. It comes from the inside where you're boiling kettles and you've wet dogs and drying clothes and making food and things like that. You might have had wet installed construction materials. You might have rebuilt something or added on to the construction, and you might have put moisture within the building itself. And then, of course, it's driven by a number of mechanisms, So the process of heating buildings can drive moisture in a certain way, or, you know, if there's air gaps in the construction, air can bring with it a lot of moisture. So there's multiple ways in which it can get in and move around and different things like that. Of course, we live in Ireland, so Ireland is generally always wet, and particularly if you think of today is where I am in Longford, it's absolutely drowning. But these are two maps. The one on the right is taken from BR 262, and which is a UK document, and it was really developed to give us some idea of the exposure of weather conditions on that island. And what you can see on that island is that some of it is actually sheltered, and a large proportion of it could be considered moderate exposure. And then it's only as you get to the kind of west and northern parts of the country that you get into the severe and very severe. Well, Joseph Little, the architect and Building Life Consultancy, developed an Irish version of the map, which is the one on the left, based on the principles of the BR map. But the main difference really is that you can see that we begin at moderate, and most of our island is covered in severe and very severe. So we're always at risk of high elevated moisture levels on building sites. This is a very, very common condition that we see. And likewise, our daily living means that we'll always have a huge amount of moisture generation generally. So if we're going to be faced with moisture at an ongoing, in an ongoing way, it's key that we address these moisture sources as closely as possible. So before we even think about insulating something, we have to think about the fact that our building must be in a weather-tight, defect-free condition that will address the majority of the risk associated with moisture. And likewise, from an internal point of view, we can't underestimate the importance of a clear ventilation strategy. So again, this CPD is not about ventilation, but generally speaking, a holistic approach to upgrading buildings will always consider ventilation as a method of source control, so preventing high elevated moisture levels from occurring internally in the first place. So there's multiple different types, of course, and you know, PARDEV gives clear guidance on what's actually necessary. So we won't get into it too much in light of the time we have today. But really what we're trying to avoid is mold, condensation. So two things that will cause that is a lack of ventilation and cold surfaces. Now, a lack of ventilation can be improved by a ventilation system, and a cold surface can be improved by insulating on a cold surface. Okay, so that's really it broken down in a nutshell. Now, the reality of it is that if the humidity is too high inside, so if you have a poor ventilation strategy, or if you don't have enough adequate ventilation internally, you'll get a high buildup of humidity inside, where that humidity within the air is almost at saturation point. And as soon as that air approaches a cold surface, like an inefficient window or a poorly insulated wall, it will condense. And then that in turn will lead to mold growth and things like that. So that's exactly what you're looking at there. And generally this happens quite a lot after IWI, so after internal wall insulation. And the key reason for that is the bits that were left out create cold surfaces inside at junctions. So what you're looking at on the left is a thermal image I'm sure you're all familiar with, where on a cold night outside, pointing the camera at the building, you can see quite a lot of heat loss at the junction. The party wall, for example, or the inefficient windows, or the space behind radiators, or the intermediate floor. And all of these junctions internally will be much colder, which is what you're looking at the images on the right-hand side. Because heat is lost there at an increased rate, the surface temperature drops in those locations, which leads to things like mold growth in the corners, between ceilings, at intermediate floors, in window reveals. These are all very, very common areas. So when you're looking at internal wall insulation, it's important that you think about the hard to reach areas. And that's really where the devil is in the detail. It's not so much about heat loss, although it does have an influence. Typically the heat loss associated with thermal bridging, there might be some very experienced people in the audience in this respect, like myself, but typically you're probably talking in or around somewhere between 10 and 30% heat loss, depending on the building. But this type of building, you'd be closer to the 10 mark. But it's not so much about that. It's more about the cold spots on ceilings, preventing mold growth, which in turn can have an impact on human health and indoor air quality. So again, when we're insulating from the inside, we're always trying to find the path of least resistance, which would be the gaps. And we're always trying to make sure that we have adequately insulated into those zones. So here's a sample of where something like this occurred. As it says there, when you're thinking about IWI, you're always trying to join the dots between upstairs and downstairs and from room to room and things like that. And it can be difficult because you can have floors in the way and walls in the way and stuff like that. So this is a good example where they wanted to insulate upstairs, they wanted to insulate downstairs, and it's two separate units. So they were insulating onto the floor from above for sound and things like that. And likewise, they hadn't intended to insulate the soffit from below. And I'm not sure how legal that was, but that was the intention at the time. But because this structural interruption was in the way, when we modeled it, we found that there was a risk of low internal surface temperatures, as low as 9.43 degrees, which is significantly lower than the allowable 15 degrees in accordance with Part L of the building regulations, which is the FRSI risk factor. So to demonstrate that just by creating a small collar underneath of the soffit to overcompensate for heat loss in that area, what we could show was that the surface temperature that was likely under certain conditions would be higher than 15 degrees, therefore reducing the risk of low surface temperatures in that area. So it's not often about how much you put on the walls. Sometimes it's about how clever are you using your insulation. Have you overcompensated in areas where it might be necessary? Actually, I'll just go back to that one. In this instance, although it was enough to do it with a little tapered slice of insulation like that, what they ended up doing was, because it was a dropped ceiling in that area, they ended up just using a standard square board for a distance of 1 meter, or actually 0.5 meter, and it was enough to prevent any potential problems in that area. So here's a good example of this as well, of a thermal bridge. It's not very apparent that it's a thermal bridge, but this is a window shutter box. So right the way up to the window shutter box is all external wall, and they insulated that with calcitherm. But they failed to recognize that this little area was also external wall. It just happened to be a pocket in an external wall, and it was where the weights for the windows and things like that were going. So they failed to insulate into there, and as a result, they got quite a bad mold outbreak, because when we close that door, it's a still air void, so there's no adequate ventilation. You know, warm, humid air can just leak in there, and it'll find the cold, uninsulated wall surfaces and just condensed in that zone. So it had poor ventilation and it had cold surfaces. Now, the homeowner rang and said, "We have a problem. I thought your calcitherm was meant to be made with lime. Does it not fight mold, etc.?" So we went out, had a look, realized it wasn't insulated. We told them, clean it down, you know, kill the bacteria, insulate it with a small piece of calcitherm. We came back a couple of weeks later, everything was fine, and it's been fine since. So just taking away one of those conditions, it still had poor ventilation in there, but it didn't have the cold surfaces anymore. So even taking away one of those things has improved the capacity of that building to fight things like mold growth and condensation. Likewise, if we're going to use the insulating material in a very clever way, we also want to be thinking about the walls. Not all walls are the same, and to be fair, some of this is quite intangible, but you know, what often happens is we don't give the credit to old walls that they deserve. You know, we tend to think of them all as just being cold. Old buildings are cold, 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 but in fact, there's a lot of evidence to suggest that that's not true. So, you know, one report here, and I know there are others, but this one is the one I usually go to, and this was carried out by Dr. Caroline Rye in 2010 for the Society of Protection of Ancient Buildings, and it looked at the U value of traditional building walls versus the theory of that versus the reality. So what they done was they just simply modeled in U value software what the U value would be of a selection of buildings. And they compared that to the in situ monitored U value performance. So they actually physically went to site and they measured it. I'm not going to go through that entire graph, but I just highlighted this one area in this red hatch. And this was a 200 mil thick granite wall, which we'd all know would be very, very cold in reality. 200 mil thick granite wall is a thin, very conductive wall type. So when you calculate the U value for that in a U value software, in the blue column, what you might see there is the 3.87 U value. But actually, when Dr. Rye monitored the performance of this, what she found was it was actually 2.14, which is significantly better. So this was actually the project in question. It was significantly better than expected. So because we're not giving it the, you know, I suppose the credit that it needs, you run the risk of over insulating this building from the inside, or at least using more insulation to think you're getting down to a U value when in fact you're probably gone much better in the first place. But all this is okay as long as the building is not wet, because as we all know, if you take out a t-shirt or a jumper out of the tumble dryer and it's still slightly damp, if you put it on you, doesn't matter how good that jumper is in normal circumstances, you'll be freezing cold because all of the temperature from your body is being used to evaporate the moisture remaining in the jumper. Buildings are no different. A wet building is a cold building. So if you allow masonry to get wet, it really is going to underperform, no matter how much insulation you put on it. So there is a skill to keeping old walls dry. Generally speaking, that starts with the pointing. If you don't have a plaster on it, it's vulnerable and it will get wet. But if it has appropriate and adequate pointing, that wetness or that dampness can drain from the stones into the mortar joints, evaporate harmlessly, and keep the building dry in an ongoing way. So it kind of stays in a cycle. But if you've poor pointing or inappropriate pointing like cement, that can really reduce the wall's ability to dry. And it can start to put vulnerable masonry like brick under duress. So things like brick can get very wet. And if you've got bad pointing or missing pointing, the brick doesn't drain adequately. And then you get freeze thaw conditions causing things like spalling, or basically the face of a brick exploding. Now, when that happens, the inside behind the crust of that brick is much, much softer. So it tends to degrade really quickly at that point. Once you get a little bit of damage, you tend to get a lot of damage relatively quickly straight after. Now, there are measures you can take. I just want to make you aware of this. You may have instances where something comes to mind if you're dealing with an old vulnerable brick that has evidence of spalling, things like that. There are breathable clear coat treatments that you can use on them that do not change the color or the texture or the appearance of the brick in any way. They don't limit moisture vapor permeability. So they don't change that aspect in any way at all. But what they do is they reduce the surface tension of the brick itself, and they make it difficult for water molecules to cling to it. So it basically falls off it. So just to make you aware that really you may see it on your travels. This is where we kind of get into the drying side of these older walls and what happens when you apply insulation to them. If you look on the top there, on the top left-hand side, what you'll see is with no insulation on the wall, when a building gets wet during rain, on the right-hand side, you'll see that it has a full drying potential, and approximately twice as much drying occurs to the outside as occurs to the inside. That's denoted by 4 hours outside and 2 hours inside. So that's the reality. And the reason for a wall having more drying potential to the outside is it has the wind. So the wind blows across the building and it encourages drying. As it dries the surface, more moisture moves into its place and it dries that too. The inside is slightly slower because you're just dealing with temperature and, small degree of air movement. Now, when you insulate a building, if you jump down to the right, to the bottom image, when you insulate a building on the right-hand side, the left-hand side, what happens when it gets wet, if you look over to the right-hand side, you've cut away the drying potential to the inside. So now you're fully reliant on the outside. So you've limited its capacity, no matter what really you use, but some things will be more favorable than others. So in a way, this kind of goes back to what tended to happen from about the 1960s on. Before that period, we were very good at recognizing that walls had full drying capacity. We used to do things like, we'd build with adequate land drainage and lime plasters that would encourage drying. So the building would still get wet, but it would dry just as quickly. And we'd have forgiving surfaces internally and externally, and we'd have good drainage and, breathable floor buildups and things like that. But from about the 1960s on, this kind of thing started happening where we put in cements and gypsums on old walls, and the walls still got wet, and it still was dealing with the same sources of moisture outside and inside, and potentially ground and sometimes. But what happened was you'd limited its drying capacity. So you'd really cut down its ability to evaporate moisture. So things like embedded timber and stuff like that were then put at risk of rot and decay and, building failure. Likewise, the same thing happened with insulation. We went down this road of these types of boards. Now, they were quick and cheap, and they were available in every local hardware in the country. So you'd go down to your local hardware and John behind the counter would tell you, we've got this pallet of stuff out the back, it's great. Paddy used it last week. He said it was class. And of course, all that was true because they didn't know. They didn't have the benefit of time and hindsight at that time. It was just the newest thing in the market. So what happened was we started insulating everything like this. Now, not only are these boards and stuff highly impermeable to moisture vapor, I mean, they don't let moisture vapor evaporate through them. So potentially they trap things behind them. They also created things like still air pockets in the zones between the dabs. Now, those still air pockets provided a space where warm, humid air could leak in from the room side. And when it did, it would find that cold, uninsulated surface. Because there's not adequate ventilation back there, it had the perfect conditions for mold growth. And this is a really, really common site where you see the mold growing between the adhesives, which is why a lot of boards should either be fully bonded to a surface or mechanically fixed. Avoid the need for dot and dab at all costs, because this is the kind of conditions it creates behind boards. So likewise, a very poor understanding of dry lining came about around the same time. And in this instance, what happened was an old farmer tried to just make his old kitchen a little bit warmer. So what he done was he framed the wall with some timber right over his gypsum plaster, which sat on top of, in some cases, mass concrete and in some cases block. Okay, and he filled that old dry lining with a small bit of insulation, like a mineral wool or something like that, and then he put plastic sheets over the whole thing, and he didn't really tape them up. He recognized someone gave him some advice that I might need a vapor control layer. He didn't really know why, so he put it up anyway, a bit of plastic, and put on his plasterboards. Now, a couple of years later, he realized he was, getting health complaints, and there was smells in the building and stuff like that. And he soon found out that it must be going on behind this. So he ripped it all apart, and this is what he found. So he was really cultivating bacteria in this instance. And you can see the way the gypsum has all completely pulverized and fallen from the substrate, because gypsum has no ability to buffer moisture at all. And because it's also pH neutral, mold will get a hold on it really, really quickly. So I use this slide to just demonstrate the gypsum is not a great background to insulate across. And likewise, if you're going to build a dry line, you've got to consider that it must be well air sealed in the first place, because if not, warm, humid air will leak behind everything and it'll get in there and get up to no good. So we look at dry lining in a bit closer as we move on. So before you insulate, there's just some things that you'd want to be aware of, and as I said, there's no silver bullet that applies to every building. So you have to build a sort of a plan that involves knowing your walls, the type of walls and where it is in the world. Is there any building defect that needs to be addressed? You can't rely on an internal finish to solve a problem. It's like a plaster on a broken leg. What are the plaster types, internally and externally? Because that'll all make a difference as well. Where are the hard to reach places? Can I insulate into them? Will they let me, lift floorboards upstairs or drop a ceiling downstairs? Or can I create a collar on an internal wall if I have to? Things like that. And then other points of note, like, can I improve air tightness as I'm, installing the insulation system, or, is there adequate ventilation in the building, or have they considered it? So all good plans will consider these things. They'll consider everything from U values to air tightness to where the thermal bridging might be, ventilation. And then I suppose the only thing we haven't touched on is, well, we did slightly. We looked at it with that image where there was problems going on behind boards. And that's really this aspect of it, interstitial condensation. This is the bit that's hard to figure out. How do we know what's going to happen behind there? Because we can see what happens on the surface if you get a bit of surface condensation and mold, but you can't necessarily see what's going on in there. So the best way to avoid those issues is predictive modeling. And when you're developing a situation or a specification for a project, it's always best to look at these things. It's always best to use best available techniques like woofy modeling. Some of you might be familiar with woofy modeling, but basically what it is it's a dynamic software that you can input, material properties and, locations, real-time data, climatic conditions, orientation, things like that. And then you can analyze, the risk of moisture, in an ongoing basis over 10-year cycles. So this kind of thing is done to an EN standard, EN 15026. And that really is a different type of dew point assessment method than the old EN 13788, which is the standard dew point assessment method. This one will take account of a lot more. The old standard method only looks at vapor moving from inside to outside. So I'd be very careful relying on the old method on anything to do with IWI. It's not very appropriate. We use it all the time, and other companies do too. And here's a good example. This is called the Sturley Barn Enerfit project, where really low U values were desired because it's an Enerfit. So they were looking for target U values of 0.11. And they had a building here that was unprotected, so it could get wet at any time because it's just exposed stone, and the aesthetic was important to them. And they had a lot of space available to them on the inside. So in this instance, they looked into really building a frame within the box, building a timber frame construction. You could call it a dry line, but it's more of a timber frame construction within that stone barn. And how they done it was they used these engineered joists and as their primary insulation zone. So they're going to fit cellulose insulation between that once the vapor control air goes on inside. And as you might see between the studs, you might see the wood fiberboard backing. That's a secondary insulation on the back of the stud. Okay. But the big question was whether or not they would get away with leaving the void between the stud and the wall exposed, unventilated. That was the key question, because to perforate that building in multiple places would have meant, using air bricks, cost, time, labor, et cetera, et cetera. So they really needed to look at this from a point of view of moisture risk. So from that point of view, we did look at it. And with WUFI, we modeled it. And what we done was we put a probe on the back of the wood fiberboard to see what would go on there, in the model over a period of time. And on the basis of no ventilation in the cavity, we carried out the simulation and we monitored the content of the external insulation. Without ventilation, the moisture content increased to over 44% after only 7 years. So that indicated a really high risk of failure, because with wood-based products, the limit is somewhere around 18%. And it met that 18% within the first year practically. So there was a very high risk of building failure had they not ventilated that void between that new timber frame and the structure. And on the basis of including a ventilated cavity, apologies for the graph, I'll explain it now in a moment, it's a bit up and down, but that's what you're seeing there is seasonal variations, wet, dry, wet, dry, wet, dry. But on the basis of including ventilation in that cavity, when we carried out the same assessment, the moisture content remained at a really stable 10.5% average over 10 years. So that indicated a really high level of safety. So things like WUFI modeling can be really useful for IWI strategies. And then just to show off a little bit, we just proposed a different strategy, use calcitherm, 100 mil of calcitherm on your walls. Now, it wouldn't have given them the U value they were looking for. It was just to demonstrate how different materials can perform so differently. So even by using 100 mil of calcitherm on the walls, like the results show like a really stable condition. The moisture content never exceeded 4% on the wall, even with the exposed stone wall and the boards directly bonded onto it. And when you think that calcitherm is essentially 91% air, it was a long way off being wet. So it just really, we use WUFI modeling to prevent issues in the best possible way from occurring potentially behind insulations. And because any good plan won't result in mold on the surface, which you can largely eliminate by insulating into the right areas, or behind stud work and things like that, which is the bit you can't see. So you really have to do, your due diligence when you're looking at this kind of thing to try and offset some of the risk, because risk will always be there. But, the trick to it all is making it as low risk as possible. So there are really 3 primary options available for IWI. You'd be familiar with all of these kind of strategies. And it's not just these products that I'll talk about. There are loads out there, but generally you can apply them in 3 different ways. There are that in the red there, and I'm going to give everyone a copy of this presentation as well, but in the red there, that's just a fancy way of saying stud dry lining, okay? So semi-rigid natural insulation pressed between stud partitions and using an intelligent vapor control air internally. That's basically what it looks like. You build your stud, you insulate the stud completely. You don't leave an airspace between the stud and the wall. And you can only do this if the wall is being plastered on the outside. So if the wall is not being plastered on the outside, the risk there would be the wall gets soaking wet, and then in the summertime, the sun is driving a lot of that evaporating moisture back towards the inside, where it meets vapor control layers and potentially not drying quick enough, putting the timber stud element at risk, etc. So if you're going to opt for a stud dry line, it's important that the outside of the building has a protective render on it. So you might be asking, well, what's the importance of the vapor control layer if it causes all that sort of issues? Why can't I just do it and put a plasterboard up? We look at that now. So it's got to do with a mode of heat loss called convection. And you'll all be very familiar with these terms anyway, so I appreciate that. But when we're looking at U values, we're only thinking about conduction. How conductive is the material? And therefore, if you've got a good U value, it must be great at preventing heat loss. But there is another way of looking at it, and that's through convection. So they've known about this for decades in the Institute of Building Physics in Stuttgart, and they study this in their labs and things. One such study that they carried out was they took a 6-inch piece of insulation and they put it under lab conditions where it was -10 outside and 20 degrees inside, with a relative humidity of 50%. And they perfectly sealed this insulation with a piece of plastic membrane. So they made it perfectly airtight, and they measured the U value and they got 0.3. So exactly what my software would tell me. So my software assumes these perfect conditions, but in the real world, there's sockets and things, and there's gaps in the fabric, and there's badly sealed connections at windows and stuff like that. So to illustrate some of that, they just cut the membrane 1 millimeter for 1 linear meter. And now they retested it, knowing full well that convection was possible. So now with the influence of convection under the same conditions, when they remeasured the actual U value, what they found was it went as high as 1.44. So just by allowing warm air to bypass the insulation or get into the insulation, it diminished its quality by as nearly 5 times. So it's hugely important in terms of heat loss to make sure if you're using a dry line with flexible, fibrous, pressed type of insulation, it's fully airtight on the warm side. Otherwise, it may not be worth the paper it's printed on. But likewise, from a point of view of controlling the internal moisture, it's hugely important also. The plaster on the outside of the building can deal with the rain, but from the inside, the moisture generation that's coming from the inside, we have to control that at source, which is why it's called a vapor control layer. So under normal conditions or under ideal conditions, that vapor can move only really slowly. It'll move by a process known as diffusion, where the tiny little particles move through the plastic at a really defined rate, and it'll be very, very slow and insignificant. And under ideal conditions, that vapor will only move at a rate of 0.5 grams of water after 24 hours. So when they measure the condensate on the back of the insulation, that's all they could find. So nothing at all. But when they ripped the membrane, to simulate your sockets and things like this, or areas where warm air might get in filled with humidity, what they found was when they remeasured it, now that convection was playing a part, they found nearly a litre of water per square metre after 24 hours was possible to get through that. That's very severe. That will lead to building failure very quickly. So it increased the risk of something happening by a factor of 1,600 times. So although the vapor control layer is important for heat loss, it really is. It's crucial for fabric safety when you're dealing with timber elements within buildings. So when you're building dry lines, it's important to have a protective plaster on the outside of your building and a well-sealed air and vapor control layer on the inside of your building. You don't want to pull the dry line off the wall where the space between the dry line and the wall is unventilated. Warm air will leak in there, and as it gets into that cold space, it'll get denser and it'll lose its moisture. And of course, we've seen the images of what can happen when that happens. So unless you can ventilate that space to the outside, top and bottom, don't do it. Press the dry line straight back to the wall and eliminate the void where potentially warm, humid air can leak into. And if you don't, a stagnant air pocket is very prone to causing this type of issue. So avoid stagnant air gaps, follow those simple rules. The insulation installed in contact with the wall. If the wall happens to have a surface on it like lime, that's ideal. because lime has got a high alkalinity. It's about a pH of about 11/12. So it'll be effectively like a biocide. Mold won't like to grow on it. Generally speaking, you keep the stud a tiny bit off the wall so you can tuck a little bit of insulation in behind it. That'll help thermally break it from the wall as well to prevent excessive heat loss through the stud elements. There's a few different ways in which you can do it. You can, build the stud with small noggins behind them, bracing it off the wall, or you can use sole plates and headers. You can install the membrane first and insulate after, or you can install the insulation first and put on the membrane after. It's just important that it's all very well sealed to floors and at gaps and stuff like that, because as we saw, like small gaps can lead to a huge amount of moisture, which can be really problematic. So sealing is critically important. And when the dry line is completely finished, it's always best to protect it with a counterbatten before slabbing so that you're not piercing it all over the place. But again, just to ram home that point, when you're dealing with this type of strategy, it's important that your walls must be rendered from the outside. So moving on to the second type of insulation approach you can use. These are just directly rendered natural systems. So you could be using wood fiber, but you could, just to be fair about it, not just being completely product heavy from us, you could use things from, other suppliers, things like cork boards, for example, and there's many other types on the market, but a breathable natural insulation system like wood fiber board. Generally speaking, they come as systems, so you don't need to know all these different parts and pieces, but they come as systems with adhesives and lime plasters and meshes and things like that. They've got really, really favorable properties in terms of water vapor permeability. They're good insulators. They're great at dampening sound and stuff like that. And they're relatively simple to install. As you can see, they're not dot and dabbed. They're tiled into position with adhesives. They're cleverly tucked into places like reveals, and they're structured in corners and stuff like that. They're insulated in the same way. They're finding the hard to reach places between floors, and they're going up between the joists and stuff like that. Before internal partitions are built, you see on the right hand side, they've already installed the boards and they've plastered one half of it into the internal partition zone, so to avoid thermal bridging in that instance. And they're relatively simple. I mean, they're just, once the wall is level with lime, it's just a board and a lime plaster with it. So that's the second option, and that will cover quite a lot of breathable board-based systems. The third option is a kind of a derivative of that. It's a similar installation approach, but instead of just using a natural insulation, it's a mineral-based capillary active insulation. And what sets that apart is how it deals with liquid water. So the term breathability can be misleading. People think breathable, they tend to put too much weight on the vapor side of things. All of these systems are breathable in terms of vapor. They'll all allow moisture vapor to evaporate through them very quickly. But what they'll do very differently is how they deal with liquid water. And that's where the capillarity of something comes into play. If you look at this time-lapse video, the wood fiber, I'm just going to go right to the end. The wood fiber on the left, the calcium silicate in the middle, and the diatonite on the right-hand side. The two from the middle and the right, they're both considered very capillary active. They can take on board a lot of water, whereas the wood fiber, despite being breathable, can't. So you don't want to put wood fiber in a situation where it's considered severe or at risk, because at the end of the day, it's a wood-based product, and you don't want to have it in a situation where it's under stress because it's in the presence of water or a building defect. So that's where capillary active systems come into play, but they're very similar in nearly every way. I mean, you still get into the hard to reach areas. They still contain adhesives and mesh coats and stuff like that, and you paint them with breathable paints. The only one that's really different is the diatonite, the thermal plasters. They're applied to exposed masonry surfaces. So whereas the boards need leveled backgrounds, these don't. These are highly insulating plasters that you can apply directly to masonry. And then you skim them and you paint them with a breathable paint. And they just contain ancient materials used in a modern way. So, earth, cork, clay, hydraulic lime, all the things are ancient materials, but they're just combined and they're completely natural. So they're very appropriate for older buildings. There's declaration of performance is available for all these, by the way. They're completely compliant with, EU standards and Part D, the building regulations. But what a lot of these systems don't have is IAB. So if you might be looking for it for grants or something like that, that's the difficulty we're finding, is that the grant process might be insisting that you use something that has IAB. Now, if you look in the market, what has IAB? You're finding plastic-based systems with metal in it and rock wools and things like that. And that's fine, and it may be appropriate in certain circumstances, but just be aware that it's not appropriate in every circumstance. There are versions of this that will help retain salts and stuff like that. I won't get into it. And as I showed before, they can be machine applied very, very quickly to old solid masonry structures and then screeded off. I'm not going to show too much of this, but one of the advantages is sequencing. You can get your electrical first fixing done and your conduits and things in place, and you can literally swallow them with thermal plaster, so long as you prepared everything in an adequate way. So in terms of sequencing, they're actually very advantageous as well. You do about 200 square meters in one day with a pump like that. So for large, old, exposed stone structures, they can be really useful. Likewise, it can be used on the outside of buildings. It has precedence in protected structures. Here's just two examples. So, there's a lot of precedence there. In terms of suitability, it's already been demonstrated. It can be used to maintain the character of older buildings like this courthouse that has a very significant character. Not looking for huge thermal improvements, but just benefits without compromising the quality or the internal finish and things like that. It can be used in very historically significant buildings like 18 Ormond Quay. This building won Europa Nostra Award, which is a European Heritage Award. And, they pulled off all the old cement renders and stuff. And they brought it back to its modern day glory. But again, as I said, the U values weren't outstanding, but all they were looking for was something to replace the first option, which is just to use lime to replaster the inside surfaces, which were all decayed and falling from the wall. Now, if they had just used lime, their U values would only improve to 1.67, which is tiny marginal improvements, but it would have been appropriate. But by using diatonite just as thin as 30 millimeters, they were able to get that right down to 0.81. Now, might not break any records, but it's still an energy saving for the building occupants. So if we're going to reuse these buildings, we need to make them useful for future occupants. Likewise, you can bond things like calcitherm or wood fiber to the thermal plaster to hit any U value you like. So if you have a very onerous target, you can use thicker layers. You may need to look at this in terms of a WUFI model. You may need to demonstrate that it's low risk to do so, but at the same time, you can combine any of these measures, or you can build a dry line to hit any U value. With all of these things, it's important to use an appropriate paint finish. You don't want to go to all this expense and then cover it with a plastic-based paint. So we got to the end, and as I said, I'm going to be giving this copy to everybody, so I'm not going to read through all of this. A lot of this is just what we talked about, and I know we're approaching the end of my time limit, so I'm not going to go through every bit of it. We can help you with a lot anyway. As technical people yourselves, we do have a big technical team that's always available, so if you need to get in touch for things like U value calculations, dew points, things like that, WUFI assessments, etc., or even further CPDs or in-house training or anything like that, just feel free to get in touch anytime. And our details are on the website, but they're here as well. We do have a great website as a resource.